Good evening, students. Welcome to another late night physics lesson. Today, I'm just going to do a few things, such as going over Newton's first law. I mentioned in class a little bit, but I want to show some applications of it. And my main goals are to kind of prepare you for the quiz that's coming up. But most importantly, above that, is to teach you physics, of course. But also to make sure you're prepared for the quiz that's coming up pretty soon. Not a whole lot of stuff on it. Just mostly it's around equilibrium of forces, drawing force diagrams, etc. My goal is tonight, what we're going to do, talk about Newton's first law, what it means, go over, let's see, a few forces such as the gravitational, the normal, friction, spring, show the balances between forces, show how to draw them, and we'll do one problem solving. Hopefully this video shouldn't take much more than around 15 minutes is what I'd like for it to be when I'm done. Okay. Oh, my goodness, my dinner. Okay, Newton's first law. You guys may remember it from class. We talked about it just a little bit, or you may remember it from possibly like another class or middle school, or maybe even like a bedtime story from your parents or something like that. Newton's first law states that an object in motion will stay in motion, and an object at rest will stay at rest unless acted on by an outside force. I'm just going to call this N1, Newton's first law. Now, this whole thing could be summed up by one word. Does anybody know what it is? We're really talking about a resistance to a change in motion. Yes. Inertia. Resistance to a change in motion is basically one word that summarizes all of Newton's first law of motion. If you ever go on to college and the professor on the sometime during your physics course says, "What is mass a measurement of?" As in, when I measure an object's mass, what am I really measuring? Well, mass is actually a measurement of inertia. Mass measures inertia. And it kind of makes sense, since considering I can go to another planet and my mass doesn't change. My force due to gravity may change, but my mass does not. And if an object has more mass, then it has more resistance to a change in motion. As in, if I push on an object, the more mass it has, the more force I have to apply to it in order to accelerate that object. So it makes sense that the mass is actually a measurement of inertia. What this means is that if an object has more mass, then therefore it has more inertia. I just want to iterate something, and when I say iterate, I mean maybe similar to something on a quiz, that more mass means more inertia. Notice I'm not saying anything about the object's velocity or acceleration. I'm just saying more mass means more inertia. So I didn't say, notice the velocity has nothing to do with that. That's all I'm saying about that. That's all I got to say about that. Okay, moving on. Newton's first law also states that forces must be equal and opposite. That means if I take the sum of the forces on an object, if it is not accelerating, then the total forces acting on it must be equal to 0. This little symbol right here just simply means sum, in case you haven't seen it before. Sum of the forces acting on an object must be equal to 0, or there will be a reaction of some kind. Now, forces, since we're going to deal with two-dimensional motion, that means I have to break the forces into 2 dimensions, which really means I'm going to have to be able to say sum of the forces in the x direction are equal to 0, and the sum of the forces in the y direction are equal to 0. Basically, my horizontal forces must be equal to 0, and my perpendicular forces must be equal to 0, or the object has acceleration. We'll deal with that when we get to Newton's second law of motion. Okay, the forces we're going to deal with, or look at today, or define anyway, are gravity. And when I talk about the gravitational force, I'm going to write F of g, and F of g actually has an equation for it. That is mg. Now, I will promise you I will derive where this equation comes from when we get to Newton's second law of motion, but I kind of need Newton's second law of motion in order to describe how we know that the force due to gravity is mg. So for now, just trust me, force due to gravity is equal to m multiplied by little g, and guess what little g is equal to? That's right, 9.81. It's not a negative 9.81. We'll use a negative or positive in front of the force symbol, but we will not put a negative right here. For this one in this unit, we'll keep it as a positive 9.81. I know that's slightly confusing considering we use the negative 9.81 in our projectile motion unit, but you just have to remember it is a 9.81. Okay, gravity, the other one, the normal force. The normal force is simply nothing more than a force that is perpendicular to a surface. So, for example, if I'm standing on the floor in my classroom, which I am, then I'm exerting a force on the floor, a gravitational force down onto the floor. Well, in order for me not to move through the floor must also exert a force equal and opposite on me, which is also perpendicular to the surface of that floor. If the force was not perpendicular, then I would go sliding across the floor. There is no equation for it. It's usually based on the other forces of being applied to the surface. All right, the other one we're going to talk about today is a frictional force. The frictional force is, is nothing more than a resistance to motion. Frictional force is nothing more than a force resistant to motion. It can exist even if the object is not in motion, as in it could be the force that's keeping the object from moving. Oh, I'm sorry, I didn't put the symbols. For the normal force, we're going to write F of N for the normal force. For the frictional force, we'll write an F of F. And one other force we're going to talk about today is the force in a spring, or also called a spring force. And for that one, I'll write F with a little s for spring. And this one does have an equation. It's very, very simple. It's actually just kind of was derived experimentally many, many years ago, hundreds of years ago, by a guy named Robert Hooke. And he came up with this thing called Hooke's Law, not Captain Hook, but Robert Hooke. And he said that the force of a spring is equal to the K value of the spring multiplied by the distance by which the spring is stretched. Then x, I'm using an x to show distance. So the force of the spring, or the strength of the spring, I'm sorry, not force, K value is the strength of the spring multiplied by the distance the spring is compressed or stretched. I can give you an example. This little cookie pin has a spring inside of it, and if I open it up, oh, there it is. Oh, there. And if I try to squish the spring, I can feel a force on my fingers that increases the more I compress the spring. And as I get the spring compressed really, really down, like really far, then I can feel the force getting really, really high. I don't want to go shooting it. Oh, almost lost the spring. Now that spring doesn't push with a whole lot of force, so therefore that spring probably doesn't have a very big K value. But if I had a much larger spring, then I would have a much larger K value, such as this one, which came out of an automobile. The K value on this spring would obviously be much, much larger than the K value on that other little spring. Okay. Oh boy, we're at 9 minutes. Keep on going. What else? I was going to draw some pictures, do some force diagrams. There we go. I'm going to draw some free body diagrams. I don't know why these are called free body diagrams. I guess it's because the object is not bolted down. I don't know what it means. Free body diagrams. All right, the first one I'm going to do is an object resting on the floor. There's this object with a certain amount of mass. The free body diagram is nothing more than a diagram of all the forces being applied or resulting on, or being applied to the object, or basically forces on the object. So for this object, downward there is a force due to gravity, so I'm going to draw a downward arrow and f of g going down. And then since it's resting on a surface, there is also a normal force going up. And if I want to put these into equation, I'm going to say that down is negative and up is positive. Since these forces are both in the perpendicular direction, I'm going to say the sum of the forces in the y direction is equal to a positive normal force, F of n, a negative gravitational force, F of g. And since the object is not going up or going down, then these are, not accelerating up or down, then these forces added together would be equal to 0. What this means also is that if I add f of g to both sides, then I get the normal force is equal to the force due to gravity. And that certainly makes sense. Newton's first law states that forces must be equal and opposite, and if I apply a gravitational force on the floor must apply the exact same force on me. Otherwise, one of us is going to go through the other, and it's probably not going to be too good for me. I don't think that floor is going to hurt much. Okay, moving on, let's do another diagram. Let's say that we have an object hanging from a ceiling. This is the ceiling or the roof. And when it's hanging by a rope. So here's a rope tied to an object with a certain mass m. I'm going to draw the free body diagram. There's a force due to gravity going down, F of g, and the rope has a tension going up. Now, I'm not going to put F of x for either of these because there's no force in the horizontal direction. I am going to do a force in the y direction equation for this one. F of y is equal to positive tension, T, negative force due to gravity, negative F of g, and it must be equal to 0. Otherwise, the object would be accelerating. The object could be in a state of motion, but it would have to be constant velocity. There cannot be any acceleration in order for it to be equal to 0. Okay. Let's say, once again, that the object is hanging from a ceiling. So here's another ceiling. And instead of a rope, this object is hanging from a stretched out spring. Now when I draw this diagram, it's going to look the same, an arrow going down and an arrow going up. The down arrow will once again be the force due to gravity, but this time the up arrow will be the force of a spring. And I can set up the same thing. I can say the sum of the forces in the y direction is equal to positive force of the spring because it's going up, negative force due to gravity because it's going down, and that oh boy, we're at 13 minutes. Okay, if I want to solve for this, I can add the force due to gravity to both sides, and I get force of the spring is equal to the force due to gravity. And if I want to go ahead and solve for this a little more, I can say kx, the force of the spring, is equal to mg, the force due to gravity. Let's go ahead and throw in some numbers here. Let's say that the distance x is equal to 0.15 meters. That means that the spring has been stretched out by 0.15 meters. Let's say that an object has a mass of 10 kilograms and little g equals 9.81, and we want to solve for the k value. Well, all I have to do now is divide both sides by x, since I know what that is and I'm solving for k, and I get k equals mg over x. Therefore, k equals m is 10 multiplied by 9.81 divided by x, which is 0.15. And when we plug this into our handy dandy calculator that we never leave home without, $654. So the k value of the spring is 654, and the units are newtons per meter. Let me just reiterate this example I've just done. I'm reiterating the importance of this, as in there might be something similar coming up on, I don't know, quiz or something. Okay, let's do one more diagram. This time we have an object on a ramp, and I want to iterate the importance of this diagram. Here's a ramp, and we're going to say down here, this is down, as in here's the negative downward direction, this is the upward positive direction on this object. So this ramp, as in a way, is resting on the floor, as in here's the floor. Okay. Here's our object on the ramp, mass m. I'm going to draw a free body diagram for this object. The gravitational force is, of course, pointing straight down. Force due to gravity going down. The normal force must be coming out of the surface, F of n. It has to be perpendicular to that surface. Must be perpendicular to the surface. And then the frictional force is opposing the object's motion, or the motion or direction it wants to go. Since the object wants to slide down the ramp, therefore the frictional force is pointing the opposite direction of down the ramp. Therefore it must be pointing straight up the ramp. Not straight up. No, it's pointing straight up the ramp. Alright, you may have to draw something like this on a quiz. Okay. Does it make sense though? Normal force perpendicular, frictional force opposing the direction it wants to go, and the gravitational force pointing straight down. Makes sense to me. If you have any questions, do please come and see me. Well, we ran just a tiny bit over, 16.5 minutes. Well, do have a good evening or a good day whenever you watch this. And if you have any questions, bring them up in class. Otherwise, I will see you guys when I see you.